without further ado, our first speaker of the day will be Ari Juels. Ari is a professor at Cornell Tech and a director of IC3, and he will talk to us about decentralized identity. So please take it away, Ari.
Okay. Thank you, Sarah. I'm going to talk today about Candid, a new platform for decentralized identity. We're developing it at IC3. This project involves the type of collaboration we particularly prize at IC3. It involves work by students in Andrew Miller's group and my group, and also a partnership with JP Morgan. Deepak Maram and Jasleen Malva in particular have been leading the project, but I'll name all of the other participants toward the end of the talk. Let me begin by discussing the vision behind decentralized identity and motivating it a little bit, and then I'll get into the details of Candid and its construction. We've all had the experience of opening a financial account of some type online, whether it be an ordinary bank account or a cryptocurrency account. And many of us have gone through the process of validating our identities in a video. Right? So what do? You show yourself in a video and you hold up to your face an identity document, like a passport or a driver's license. Right? But no, not like that, because you're then covering the identity document. We can't see all the information on it. And no, not like that. You don't want to hold it up to your face because then we can't see your face. So yes, do it just like that, hold still, or do it like this. The point I'm trying to make is that this is a burdensome process, and it's also one that is prone to fraud. It's not so terribly difficult to forge a paper or plastic identity document in a way that is going to make it look plausible via video. And technologies like deepfakes are in fact making it possible even to impersonate users, impersonate their faces and facial expressions via video. So the methods we're using for identifying users online today are pretty poor and likely to get worse in the face of improving techniques like deepfakes. The basic idea behind a decentralized identity system is the following. A user can go to some authority, generally known as an issuer, and request what's commonly referred to as a credential, like an identity document. The first thing that the user does is generate a key pair, private key and public key. The issuer then digitally signs the credential, for example, driver's license here, digitally signs the credential and binds it to the user's public key. This means that this digital identity document is now effectively in the hands of the user, in the control of the user, in the following sense. Suppose that our user here, Alice, for instance, wants to apply for a loan at a bank and needs to prove a few things about herself, like her name and her age, or at least the fact she's over 18, so she can engage in a legally binding contract, and perhaps her state of residence. What she can do is use her private key now to sign her challenge from the bank to prove that this is her identity document. Right? And now the bank receives the assurance it's interacting indeed with Alice, and it can read the identity document to glean other information about Alice required to determine whether or not it wants to make the loan. And as you see, a lot of the messiness of this form of, involved in this form of video authentication goes away. If all of this works well, then it makes for a nice user experience. Interest in decentralized identity is pervasive in the tech community, and even among well-established companies. An organization known as the Decentralized Identity Foundation, which is promoting a vision and developing standards for decentralized identity, includes dozens of members, ranging from insurance companies to payment providers to startups that are providing decentralized identity solutions. And beyond the Decentralized Identity Foundation, there are a lot of other efforts arising around decentralized identity. W3C is developing a standard. Hyperledger Indy is a collection of tools in Hyperledger for the construction of decentralized identity systems. And there are a whole bunch of startups working on decentralized identity. Evernym and Uport are just a couple of them. Why this interest? Well, one obvious benefit of decentralized identity is the one that I've already suggested, namely that when a decentralized identity system works well, it can greatly improve the user experience of proving identity online and reduce fraud of the type that I also mentioned. But the vision goes beyond the mere presentation of identity documents. The credentials that a user amasses can include, in principle, any type of data. So a fully functioning decentralized identity system can, in principle, allow users to manage their own data, many different forms of data, to take control of their own data and their own privacy. Another potential benefit is that a decentralized identity system can make it easier for organizations to issue credentials to users. So for example, NGOs can issue credentials to stateless persons without having to spin up all of the apparatus required to produce forgery-resistant plastic or paper identity documents. And finally, now, in many cases, enterprises are not interested in infringing on users' privacy. They actually don't want to hold PII because it increases their liability in the case of a breach. So the enterprises, in many cases, would like to see sensitive data held by users. They don't want to touch it. Decentralized identity, obviously, would facilitate this type of custody by the user. And sometimes decentralized identity systems are referred to as self-sovereign identity systems, again, reflecting the idea that the user takes control. But we found in reviewing decentralized identity standards and architectures that many of the critical problems involved in realizing a decentralized identity system get swept under the rug. And I'll name 3 of them now. The first is the basic problem of credential issuance. So I said, suppose that Alice wants to obtain a digital copy of her driver's license. She goes to an issuer, like the California DMV, and she gets the issuer to provide her with this digitally signed credential bound to her public key. Well, that's all well and good, but where's this issuer going to come from? The California DMV is unlikely to issue digitally signed driver's licenses anytime in the near future, to the best of my knowledge. And in general, it's not clear where issuers are going to come from. It seems unlikely that a collection of issuers will simply spring up out of the woodwork before a decentralized identity ecosystem has been become fairly well established or become mature. But conversely, a decentralized identity ecosystem can't mature unless there are issuers around to produce the credentials that users need. In other words, we have a basic bootstrapping or chicken and the egg problem here. And this really doesn't get addressed in virtually any of the materials we've seen on decentralized identity. A second problem that gets swept under the rug in lots of different systems, and not just decentralized identity systems, is the challenge of key management. I said that the user has this private key, and it's by merit of her holding this private key that she can prove that a document belongs to her. The problem is users are terrible at key management. Users in general are very bad at maintaining secrets. Some of us who've custodied our own cryptocurrency have gone through the process of writing down seed words on a piece of paper and putting the piece of paper in a safe deposit box and so on and so forth. It's very burdensome and there's lots of room for error. But this problem is really not explicitly addressed in decentralized identity standards. It's so problematic in the case of cryptocurrency that it's estimated that on the order of 4 million Bitcoin have disappeared forever because users have lost their keys. Today, at least when I last checked, something like $40 billion in value has just gone poof because key management is so hard. Or to view it another way, the goal of decentralized systems like Bitcoin is to move us away from centralized financial systems. But many holders of Bitcoin take their Bitcoin or other cryptocurrency and deposit it in, or perhaps buy it directly from Coinbase. Something like 10% of all Bitcoin circulation are held in Coinbase. So we go through all the trouble of creating this decentralized system, and then because key management is so hard, we go and re-centralize it, defeating the whole purpose of the exercise. All this is to say key management is really hard. It's hard for cryptocurrency, and it's going to be hard for decentralized identity systems. Another problem that gets swept under the rug, a somewhat subtler problem, is the problem of Sybil-resistance. In other words, ensuring that a user can't assert multiple independent identities in the system. Now, Sybil-resistance is relatively easy if you don't worry about privacy. Right? It's achieving Sybil-resistance in conjunction with privacy that's hard. If you don't care about privacy, then whenever you interact with a user, you simply have the user provide an identity document with her name and address and so on and so forth. And then you can deduplicate users, as it were, on the basis of their biographical information, or perhaps even a unique identifier like a driver's license number or a social security number. The question is, can we achieve Sybil-resistance without privacy? Or rather, with privacy, because privacy is of paramount importance in any decentralized identity system. In order to describe how Candid works, I first need to introduce an important building block, actually two building blocks. The first of these is a system called Deco. Deco stands for Decentralized Oracle. Deco takes aim at a problem that I'll call the web data transfer problem. I'll give you a hypothetical scenario to describe the problem. So let's suppose that Bob has some new token, Bob's bubble token, that he would like to offer for sale. But he wants to make sure that people are buying his token responsibly. So he requires that anyone participating in his ICO demonstrate that she or he have assets of at least $5,000. All right, well, this is all well and good. Alice wants to participate in the ICO. So she looks up her bank account balance, and lo and behold, she has more than $5,000. She's got almost $9,000. This is great. So she goes to Bob and she says, Bob, I've got more than $5,000. I'd like to participate in your ICO and I am eligible. Well, Bob's next question, of course, is, can you prove it to me? Here's where the challenge comes in. Now, Alice could send a screenshot. Right? Alice can see, and she knows because she's logging into her bank website, she's got more than $5,000. She can see this. She can send a screenshot to Bob. But of course, the screenshot is worthless because Alice can forge the screenshot herself. Now, when Alice logs into her bank account, she is almost certainly logging in using HTTPS. It's her client machine has established a secure connection, a TLS connection with the bank server. Her client engages in a so-called key exchange protocol with the TLS server. This establishes a shared key, and the fact that shared is important, as you'll see in a moment, shared key between Alice's machine and the bank's machine, and then data sent between the two is encrypted and MAC'd, digitally signed in a symmetric way to ensure its integrity. So Alice, when she gets data from the bank, knows that the data actually came from the bank. Right? Additionally, the bank has a certificate, and in the course of the key exchange protocol has proven that this is its certificate using public key techniques. So she has a secure connection to the bank. She knows that the data she's getting are indeed authentic. The problem with TLS is the following. So the key exchange protocol, this protocol that establishes a shared key between Alice, the user, and the TLS server, uses public key cryptography. As I said, the bank proves its identity using a certificate. It actually digitally signs something, so Alice knows she's talking to the bank. But for the sake of efficiency, Alice and the server then communicate using a shared key. They use symmetric key cryptography for the session between them, the record layer. The data that's being exchanged between the two is MAC'd, a message authentication code is applied, rather than digitally signed. MACing is a symmetric key analog of digital signing. You can think of this as signing with a shared key. So this is perfectly fine as far as Alice is concerned when she's trying to determine that information coming from the bank is authentic. She knows she didn't forge the information, although she could have, because the key that the bank has used to sign the information is one that she has. She knows she didn't forge the information. But forwarding data from the bank to Bob is effectively no better than sending a screenshot, because again, this key is shared. Alice has the key and can produce information that looks like it comes from the bank for all intents and purposes. So TLS doesn't address this problem of relaying data to a third party. How can we solve this problem? How can we enable Alice to prove to Bob that indeed she has a balance of $5,000? Well, I mentioned servers already have certificates. And so in principle, they can digitally sign data. There's a public key infrastructure enabling users to ensure that certificates are authentic. This approach is one advocated in a very nice system produced by Sergeant Chapkun's group at ETH Zurich called TLS Notary. TLS Notary is a modification to a server that allows the server to sign data using its existing certificate. Similarly, there is a standard called OpenID Connect, an adjunct to OAuth 2.0 that does this for certain types of data. And in a limited privacy model, OpenID Connect allows servers to digitally sign data so that users can relay it to a third party. The problem with both of these approaches is that they require server-side modification. And OpenID Connect is somewhat widely used, but not universal, and certainly not universal as far as the types of data that are typically signed by servers using it. So we still have the chicken and egg problem. Servers aren't going to sign data until there's a good motivation, like a decentralized identity ecosystem, but we can't have a decentralized identity ecosystem until, well, there's somebody authenticating the data that users need for their credentials. Deco tries to solve this problem. Right? And whoops, what Deco aims to do is the following. Aims to allow Alice to log into her bank account over a TLS connection and then prove in zero knowledge statements about the data she gets from the bank to a third party like Bob, to a verifier. But didn't I just say that TLS can't do this because of the use of symmetric keys to sign data? Didn't I just say this is impossible? On the face of it, it seems impossible. The way that Deco sidesteps this impossibility is using what we refer to as a three-party handshake protocol. So here I'll assume the use of CBCH MAC. I'm going to assume a cipher suite that's supported in one version of TLS or older versions of TLS, TLS 1.2, for instance, not TLS 1.3, but Deco can also support TLS 1.3 and its GCM-based cipher suite. The key idea here is that this MAC key that allowed Alice to forge information in relaying it from the bank to Bob is going to be split between the prover and the verifier. So initially, at least, the prover will not actually have direct access to the MAC key. Schematically, this is what the protocol looks like. The prover and verifier get together and communicate with the server through the prover. And at a certain stage of the protocol, the prover and the verifier each have two halves of the MAC key. But again, the prover doesn't have direct access to the full MAC key. So they're sharing the MAC key. Give you a little bit more detail, although I don't want to get into a great deal of detail, as this is just a building block. What happens is that the prover and verifier each supply two halves of a public key during the key exchange protocol. The verifier provides its half to the prover combines the verifier's half with her half, exploiting homomorphism in the underlying group. And the result then is that they have a shared private key in the course of the key exchange protocol. The meat of Deco, the innovation as it were, is a secure two-party computation that takes this shared private key that the prover and verifier, Alice and Bob, now have, and converts it into a shared MAC key. This is the innovation. This is where a lot of the novel techniques in the paper, including a combination of binary and arithmetic circuits and a way of computing an EC group-based sharing of the private key into an additive sharing in the underlying field, these things come into play. But again, I won't get into details. The important point is, again, that Alice and Bob share this MAC key for the TLS session, so Alice can't forge data from the server, but she can prove things about the data to Bob in zero knowledge. And again, I won't get into details, but at a certain stage, the MAC key can be released to the prover after she has committed a ciphertext to the verifier. But again, the key idea here is that because Alice doesn't have direct access to the MAC key, she can't forge things, she can prove things about data from the server to Bob. Very important here is the fact that the server doesn't need to know that this protocol, this 2PC protocol between the prover and verifier is happening. The server just sees an ordinary client from its perspective. It doesn't need to know that the public key used by Alice as it sees it in the key exchange protocol is actually the composition of shares from Alice and Bob. All of that is hidden under the covers as far as the server is concerned. So the server doesn't need to be modified in any way to make all of this work. That's how the protocol works when Alice wants to prove something to a single verifier. She wants to prove something to Bob, for instance. But the real power of Deco is particularly visible in cases where we have a committee of verifiers, where you can think of this as an Oracle network. Now, suppose we have a bunch of nodes and we believe that a majority of them are honest or some threshold are honest. Alice then can prove using Deco statements about, say, her bank account, a statement about our bank account, to the different nodes in the network, to the different nodes in this committee. And they can then digitally sign a credential saying that they saw legitimate proof from Alice. And if you believe that a sufficient number of these nodes are honest, this digitally signed credential is strong evidence that Alice's claim is correct. So effectively what's happening here is that the committee of verifiers, or the Oracle nodes, are taking data from a web server and converting it into a credential that is digitally signed and therefore can be relied upon by a third party. Alice, for instance, can give this digitally signed credential to Bob. He sees the signature from the committee and he knows that Alice proved her bank balance is more than $5,000. So Deco is effectively achieving this type of conversion. You can use Deco for this purpose. Alternatively, you can use a different Oracle technology, namely Town Crier, which I'll describe in a nutshell. Town Crier leverages what's known as trusted hardware or trusted execution environment, to be more precise. This is an instruction set architecture extension available in most recent model Intel CPUs that allows an application to run in an environment that is secure in two senses. The environment protects the integrity of programs executing in it and can attest to a third party that this integrity is protected. And it protects the confidentiality of the program, as the program can keep secrets. And this protection, if you trust the hardware, is very strong. It applies even to the owner of the host, the owner of the machine on which the application is running. If we run town crier in such an environment, in an enclave as it's known, then a user can execute a TLS session that terminates in the enclave, terminates with the town crier application. And the town crier application then can observe the data that the user fetches from the bank and can then directly produce a credential, a trustworthy credential that reflects the data that the user fetched. So town crier can directly produce a signed credential proving that Alice has a bank account over $5,000. No need for a committee that in this case, although you might want to use one to hedge against failures in the trusted hardware. And there are other approaches you can take. Now, not everyone trusts trusted hardware, which is the reason for enabling the use of Deco in Candid as an alternative. Candid is a strictly cryptographically based alternative to town crier. Town crier is more performant though, as you'll see. Okay, we now have the background to understand how Candid itself works. The basic setup is as follows. Candid involves the use of a committee, analogous to the committee in a permission blockchain. And of course, we need to assume that some fraction of nodes, like a majority or 2/3, are honest. These nodes will have a few jobs in Candid. One is to securely store secrets, which they do via secret sharing, or can do via secret sharing. They'll also securely store identity data of a particular type that I'll mention. And they will also have the job of verifying proofs, verifying Deco proofs, for instance. Credential issuance, now that you understand how Deco works, is actually conceptually quite straightforward in Candid. User wants to obtain a credential. She simply performs the Deco protocol with the members of the committee while logging into target websites that she and the committee agree upon. And so the committee, for instance, may be willing to generate a credential saying Alice is over the age of 18 if she's logged into the Social Security Administration website and some DMV website and some bank website. At that point, it will sign a statement saying, a credential saying that Alice is over 18. And with Deco as a building block, as I said, this is pretty straightforward. The effect is that we're able to turn any web server into a Candid issuer. And that's how we solve the bootstrapping problem in Candid. Other features I want to highlight, although I've mentioned them before, is that because of the use of zero knowledge proofs or potential use in Deco, the committee only needs to learn from the user, from Alice here, the data that are attested to in the credential. So if Alice is just trying to generate a credential, it says she's over 18, committee members need learn nothing more than the fact that Alice is over 18. And they may not even learn that Alice is Alice, that that's her name. We get legacy compatibility here, right? Because this is inherited from Deco. There's no need to modify web servers to do this. And because of the flexibility of Deco, the fact that we can draw in principle on any type of web data, we can issue essentially unlimited types of attestations or credentials. Whatever data are available can be turned into a credential. How do we address the key management problem? The approach in Deco looks very much like the approach for issuance of credentials. But the idea is that Alice will store her key with the committee. Remember I said that the committee has the ability to store secrets securely, to do it using secret sharing. So she stores her key with the committee for backup Otherwise, she can keep the key on her local device and just use it as needed. And now if she needs to recover her key, she goes to a bunch of service providers that she has pre-registered, logs in, and uses Deco to prove that she's logged into these service providers successfully. If she provides a proof of valid login, then the committee can send her the key that she's used to back up. Now, you may ask, why don't we just use OAuth for this purpose? Isn't this what OAuth was designed for? The reason we use Deco in Candid is because of privacy. The transmission of an OAuth token leaks information that we think would be undesirable in a decentralized identity system. The committee nodes here learn the service provider ID, which may or may not be serious, but they also learn, the name of the service provider, but they also learn the ID of the user in the target service in many cases. And that can potentially be used to determine the user's real world identity. And the privacy leakage is bidirectional also in the sense that the service provider learns that the user is now recovering a key from Candid, which is also undesirable. The Deco solves both of these privacy, or addresses both of these privacy concerns. We also address the problem of Sybil-resistance in Candid, and we do this in a privacy-preserving way. What Candid does is allow for deduplication of user credentials in a way that doesn't betray user privacy. I'll describe the two different approaches we take to Sybil-resistance in Candid. The first we refer to as the unique ID approach. And the idea here is conceptually fairly simple. Let's suppose that users have unique identifiers. For instance, numerical identifiers like social security numbers, which most inhabitants of the US have. The Candid committee uses a pseudorandom function, which computes using secure multi-party computation, to convert the social security number of the user. So the committee here shares a PRF key. They use this PRF key, use a PRF, to convert the social security number of the user into you can think of it as kind of an obscured or blinded representation, a PRF representation that without knowledge of the PRF key does not leak information about the social security number itself. And to deduplicate then, Candid takes the following approach. All registered users have these PRF concealed social security numbers registered in a list that's maintained by the committee. And this list in principle can even be made public. The use of a PRF protects the underlying social security numbers. When a user wants to register, her social security number is run through the PRF. PRF value then is checked against this registration list. If it's in the registration list, it means this user has already registered and therefore should not receive a new credential. If it isn't in the list, then the user gets to register and this new PRF SSN gets added to the list. Right, so you can think of this as like the list of PRF values that's used in Zcash to protect against double spending. There's a close analog. We get an interesting form of security here in a fairly aggressive trust model. Even if the PRF key leaks, right, the committee gets completely compromised, it will be possible to crack social security numbers, but an adversary that is able to crack this list of social security numbers gets nothing but the social security numbers. There's no linkage in the list to real world identities or to the credentials issued to users. So even in the case of this catastrophic failure, you don't actually get a catastrophe. That's the approach I've just described, the unique ID approach to deduplication or Sybil resistance, is the cleaner approach, let's say. But it's not universally applicable. Some people lack unique national identifiers because their countries don't provide them, or maybe they don't have clear national identity, stateless persons or refugees, for instance. Additionally, there are many systems like sanctions lists, which I'll talk about in a moment, that identify people on the basis of biographical information, not unique identifiers. Biographical information like name and address, nationality, date of birth, and so on and so forth. So an example would be the sanctions lists maintained by the Office of Foreign Asset Control in the US. This is a list of people who are prohibited from interacting with the US financial system, people and organizations. Now, biographical data are prone to small errors, things like typographical errors or transliteration inconsistencies. The name is transliterated from one language to another. It can happen in different ways. So to work with biographical data, we need a technique for fuzzy matching, something like edit distance. Here are a couple of examples, Starbucks cups. So you see the name Cass has been rendered as cats. There's an edit distance of 1 between the real name and the corrupted name here. But the two would match in a fuzzy way. Or Ariel has been rendered as alien. There's an edit distance 2 error. Of course, edit distance type errors can involve insertions and deletions as well. But this is just to give you a sense of what these corruptions in practice might look like. Now, computing edit distance between two strings, when you know the strings explicitly, is fairly easy. But doing this over private data turns out to be rather hard. If the names over which you want to do the fuzzy matching are secret shared, then you encounter a substantial technical challenge. And this is one that we address in Candid using secure multi-party computation. And the paper involves the introduction of a number of what I think are interesting techniques, like the use of C-shingling, which has been used classically to compare documents of all sorts as a preliminary filter to whittle down the list of the set of candidates in the list against which you do edit distance comparisons. I encourage you to look at the paper for additional details. But the end functionality is the following. To perform deduplication to achieve Sybil-resistance, the committee can store a list of registered names in secret shared form, using the gray box there to denote the fact that these names are held privately by the committee. When a new user wants to register, she or he, in this case, provides a name, again in secret shared form, to the committee. And the committee can check whether this presented name is similar in an edit distance sense to any of the registered names. And if it is, prohibit the user from registering or require some additional certification to ensure that a name or an identity is not being inappropriately duplicated. This ability to perform fuzzy matching is also useful for accountability or revocation. For example, for proving that you're not on a blacklist, like a sanctions list. What a user can do, and Candid requires or can require this of users at the time of registration, is prove in zero knowledge, and we don't need MPC for this, prove in zero knowledge that the name you're trying to register in a new credential, as you're establishing a new identity, does not appear on a blacklist of some type. Again, like a sanctions list. So Scrooge McDuck at the time he's registering can prove that his name, which is presented in, again, a privacy preserving way, doesn't appear on this list of known bad guys. Now, MPC is still useful for proving that users are not on blacklists retroactively and for revocation of identities. Blacklists, of course, change over time. So the fact that a user proved at the time she registered she wasn't on this list is insufficient to maintain the integrity of the service. As the list evolves, as new names appear, those new names need to be checked against registered names. And for this purpose, we can use the MPC-based version of fuzzy matching available in Candid. Let me summarize here by taking a step back and briefly discussing the life cycle of credential issuance in Candid. To register with the system, the first thing the user does is port data from a legacy system using Deco or Town Crier and create what we call a pre-credential. This is a fresh credential which has not yet been deduplicated or vetted in the Sybil-resistance protocol. User takes this pre-credential and then performs the deduplication protocol with Candid, using a social security number or using biographical information to generate what we call a master credential. This is a basic credential that has gone through this deduplication process. At that point, the user can link additional credentials to the master credential. The master credential may just reflect, for instance, social security number, biographical information. User can amass other information, age, bank account balance, whatever she likes, and attach them to this kind of foundational credential. These context-based credentials then can be presented independently of the master credential, but the master credential is invoked in the presentation protocol to ensure that the user isn't asserting multiple identities. In other words, context-based credentials inherit the Sybil resistance of the master credential. And then finally, as I mentioned, if we want to employ blacklists to ensure that users who are prohibited from registering with the system are indeed blocked from accessing it, we need to be able to revoke credentials retroactively. Right? We need to be able to perform the type of fuzzy matching I mentioned, or to use unique identifiers to identify users who are already in the system that have freshly appeared on a blacklist, or need to have their credentials revoked for some other reason, like they've lost their private keys. We allow users also to initiate their own revocation process. So that briefly is the life cycle of the credentials in Candid. We've done end-to-end performance measurements of Candid, and here are the execution times for the basic operations in the system. These need some explanation. To generate a pre-credential that reflects, for instance, social security number, using a login to the Social Security Administration website requires first an offline process for the secure computation. This offline process, this offline computation can be done before the user goes to the SSA and fetches credentials and so on and so forth. So before the user actually attempts to register. The amount of time required for this process depends most critically on the bandwidth of the user's device. So in a relatively low bandwidth setting, kind of home internet setting, this process requires about 8 minutes. Again, it's offline, so it can be done before the user attempts to register. The user doesn't need to know about it, it can happen with the covers, but something like 8 minutes are required to register his credential. In a high bandwidth environment, this pre-processing, this offline phase can take a matter of just a few seconds. The online phase for obtaining credentials, you see, is relatively efficient, requiring just under 9 seconds with, and all of this is with Deco. Somewhat costly is producing a proof that you're not on, say, a sanctions list. So we generated zero-knowledge proofs using the techniques I've described before, and with a list of something like 25,000 names. I think that's the length of the rough length of the OFAC sanctions list. Generating this proof requires something on the order of 25 minutes. Okay? But this can be parallelized, so at least the time involved can be reduced substantially. All of these things, with the exception of generating that proof, are much faster if you use trusted hardware, if you use Town Crier. and you don't need an offline phase to do it. But again, the catch is if you're going to use trusted hardware, you need to trust the hardware. Okay, that's essentially it for my presentation. I just want to mention all the people involved. Deepak and Jasleen were the first two authors of the paper. Tyler, who is the research engineer on this project. Nurla Jean-Louis and Sasha Froloff, other students, and Fan Zhang, who was formerly a student and has just received his PhD. Andrew Miller, and our colleagues at JP Morgan, Christine Moy and Tyron Lablon. We just released the paper today. It would encourage you to read it and feel free to email us with questions. You'll find the paper on my personal website and we've submitted to ePrint, so it should appear there sometime in the next few days. Thanks very much.
Great, thank you, Ari. Yeah. Thank you, Ari. That was great. So we have one question in the Q&A from Amit. Amit, do you? I don't. Sarah, if you could unmute Amit, if you want to ask the question yourself, or I can read it if I.
Hi, can you hear me?
Yeah.
Yes.
Yeah. No, nice talk. Great talk.
Thank you.
I had one question. So, is this entire scheme based on the assumption that it is easier for a user to participate in an MPC or let's say buy a piece of SGX compared to him holding a piece of card in front of the camera?
Well, as I mentioned, there are a few benefits to decentralized identity systems over, we'll call them legacy systems. One is convenience. If the user has already amassed her credentials, she can present them fairly easily. And remember, of course, that the secure computation protocols I've described are happening under the cover. The user doesn't need to participate. All this just happens seamlessly, ideally, in an app running on the user's phone or desktop machine. But as I said, the benefits of decentralized identity are not just convenience, but also resistance to forgery and fraud. As I mentioned, it's fairly easy to create a valid looking identity document, one that is valid looking via video. And that type of forgery poses a threat to the integrity of this system that is being used today to verify identities online. So I do actually think that in the aggregate, if we have a smoothly functioning decentralized identity system, it will be easier for users to present their decentralized identity credentials than to engage in this video protocol, which sometimes fails because of mistakes of the type I mentioned, where you don't hold the card right, so on and so forth.
Right, right. So is it also clear that how easy is it to use like these techniques of deep fakes to forge your credentials compared to, let's say, the kind of forgery that might happen if the honest majority assumption in MPC gets violated for some reason, or let's say the SGX has some errors or vulnerability?
Yeah, in some sense, those two trust models are incommensurable, but I would argue that it is harder to corrupt a collection of authorities than it is to use some off-the-shelf deepfakes tool to produce fake video that will persuade a validator that you're asserting a valid identity.
Right, right. One last question. So who actually selects these MPC nodes? So, you said that there will be some honest majority assumption in the MPC committee. So who exactly selects those nodes in the committee?
That's really up to whoever is creating the decentralized identity system. So they could be high staking nodes in a permissionless system. They could be a collection of companies that band together to provide a decentralized identity solution. That's really, as I said, up to the creators of a particular decentralized identity ecosystem.
Okay, thanks.
So we don't treat that particular issue in the paper.
Right, okay, thanks a lot.
Okay, up next, I think Bastien, looks like you have your hand raised.
Yeah, hi, Bastian from Utu. I've got a question about the key management. So you mentioned that when you use Deco to retrieve your backup key, you can prove that you are you in some sense by logging into different sites. You had the social media examples. And then you also mentioned that as opposed to OAuth, the verifier then don't actually learn your identity on these sites. So they don't learn your Facebook username or your Twitter username. But I don't really understand how you are sort of proving your identity there without revealing your identity.
Well, you can register your ID in a secret shared way with the committee and then prove that you're logging into an account that corresponds to this confidentiality protected ID, as opposed to producing an OAuth credential, which has the ID just sitting there. That make sense?
Okay, so you prove that you are logged into Twitter as some username without actually revealing that username?
That's right. Not revealing it explicitly, right? You are linking the ID in the current login attempt to one that you registered for the purposes of key recovery, but you don't need to reveal it explicitly to committee members.
Cool, thanks.
Sure.
So Ari, I had a question about key management as well. So it seems like the solution of secret sharing among the participants works well in the case of a user losing their key. But I'm also wondering if there are any solutions here in the case of key compromise. So if someone just compromises my device, can they effectively steal my identity? You know, would you say this is easier or harder than in the kind of real world or whatever, in usual solutions?
Yeah, unclear, but we can instantiate pretty flexible revocation policies. So revocation might look very much like the process of key recovery, where you say, I'm going to log into some subset of these service providers to prove my identity to revoke my key should it ever be compromised. And then what you're effectively doing is leveraging or bootstrapping from whatever authentication mechanisms these service providers use to prove your identity to the system.
Okay, I'm going to take advantage of the fact that no one else seems to have questions to ask maybe a slightly more involved question. So, yeah, obviously proving non-inclusion of something is quite expensive, which I guess is why you see that it takes a long time to generate the zero knowledge proof that you're not on the list. So one idea, I guess, is if you had someone running the list, not as a list, but as like a verifiable map, meaning you could do like Merkle proofs of non-inclusion effectively. Is that something that you would view as promising?
There's actually a ticket about that on the Zcash track. Zcash GitHub. So yeah, there's a way of doing it using buckets at the leaves of the Merkle tree, which is more efficient than the obvious way.
Okay.
Yeah, so we did explore the use of various data structures, but obviously we're happy to take advantage of whatever advances rather there are in this space to improve the system.
Cool. Do we have any other questions?
Yeah, so this seems like it could be really useful to the future of credit in decentralized finance. But for people who live in areas without social security systems or in-place identity systems that can really be relied on by by banks basically. So if I lived in a country that didn't have a social security system that was really trustable, would it be possible in the future for a, like what would be the ability for someone in a place like that to get a decentralized ID?
Well, we've tried to make the system inclusive in the sense that we provide deduplication methods based on unique identifiers, but also on biographical information. Now, of course, to enroll using biographical information in the system, you need to be able to access trustworthy biographical information on a server somewhere. In the absence of such information, you would need an independent issuer to be recognized by others in the ecosystem. And as I mentioned, part of the vision for decentralized identity more generally is to enable NGOs, for example, to act as issuers for refugees and stateless persons. So in some sense, this scenario is baked into the larger vision for decentralized identity. The last mile problem is always hard, though, and I'm sure there are subpopulations it would be difficult to enroll in a system of this kind. But on the other hand, it's those disenfranchised people that decentralized identity as a vision is trying to provide tools for.